Hello, and welcome to Learning Outcome 2, Understanding the Principles of Algorithms. In today's session, we will explore the question, have you ever wondered how computers solve complex problems so efficiently? The answer lies in algorithms, the step-by-step procedures that form the backbone of all computer programs. This video will guide you through the core principles of algorithms, their historical development, and their importance in modern computing. You will discover how algorithms drive problem solving, optimize performance, and shape the way technology functions in our daily lives. An algorithm is a set of step-by-step instructions designed to perform a specific task. Each step must be clear, finite, and executed in a specific order. Algorithms determine how efficiently data is processed and problems are solved. They are essential because they provide a structured approach to problem solving. Understanding algorithms is crucial for effective programming. A good algorithm must be clear and simple, with each step easy to understand. It should have a clear starting and ending point, ensuring finiteness. Definiteness is key, with each operation precisely defined. It must take inputs and produce outputs efficiently. Correctness ensures the algorithm produces the expected results for valid inputs. Algorithms can be classified based on their problem-solving approach. Sequential algorithms execute instructions in order, while iterative ones use loops. Recursive algorithms call themselves to solve smaller problems. Divide and conquer algorithms break problems into subproblems. Greedy and dynamic programming algorithms optimize choices and problem solving. Developing an algorithm involves several stages. Start by clearly defining the problem to be solved. Identify the inputs and outputs required. Design the logic by breaking the problem into logical steps. Choose a representation, such as flowcharts or pseudocode. Test and validate the algorithm with different datasets. Algorithms can be represented using pseudocode or flowcharts. Pseudocode combines plain language with programming structure. Flowcharts use symbols to show the flow of operations. Common symbols include ovals for start or end, and rectangles for processes. Diamonds represent decisions, guiding the flow. These tools help visualize logic before coding. Algorithms provide structure and order to problem solving. They improve program efficiency and performance. Algorithms aid in debugging and understanding program flow. They enable automation and decision-making processes. Fields like artificial intelligence and cybersecurity rely heavily on algorithms. Efficiency measures how well an algorithm uses time and space. Time complexity shows how running time increases with input size. Space complexity measures memory usage. Efficient algorithms handle large data volumes quickly. Industries like finance and healthcare benefit from efficient algorithms. The term algorithm originates from Persian mathematician Al-Khwarizmi. Early mathematical algorithms were used manually, like Euclid's algorithm. Charles Babbage and Ada Lovelace pioneered mechanical computing. Alan Turing and John von Neumann formalized computing principles. Modern algorithms power fields like artificial intelligence and machine learning. Algorithms must have finiteness, ending after a limited number of steps. Definiteness ensures each step is clearly defined. They require inputs to process and produce outputs. Effectiveness means steps can be performed using basic operations. These characteristics ensure algorithms are practical and functional. Brute force tries all possible solutions, while greedy algorithms make local optimal choices. Divide and conquer splits problems into parts, and decrease and conquer reduces problem size. Dynamic programming reuses subproblem results, and transform and conquer simplifies problems. Each technique offers unique problem-solving approaches. Brute force tries all possible solutions to find the best one. It's simple but often inefficient for large datasets. For example, password guessing tests every combination. It's useful for small problems or when efficiency isn't critical. However, it's extremely slow for complex problems. Greedy algorithms choose the best option at each step. They work well for optimization problems. For example, Dijkstra's algorithm finds the shortest path. However, greedy choices don't always lead to the best solution. They are ideal when local choices lead to global optima. Divide and conquer breaks problems into smaller subproblems. Each subproblem is solved independently. Merge, sort, and binary search are examples. It's efficient for large problems that can be split. However, recursion can increase memory usage. Decrease and conquer reduces problem size at each step. It's simpler than divide and conquer. Insertion sort and binary search use this method. It's efficient for problems that naturally shrink in size. However, it may not scale well for very large datasets. Dynamic programming breaks problems into overlapping subproblems. It stores solutions to avoid recalculating. The Fibonacci sequence and knapsack problem use this technique. It greatly improves performance over recursion. However, it requires additional memory storage. Transform and conquer changes the problem into a different form. Balanced binary search trees and Fourier transform are examples. It's effective when the transformed problem is easier to solve. However, transformation can add processing overhead. Understanding the right transformation is crucial. Flowcharts visually represent algorithms using standardized symbols. They show operations, decisions, and data flow. Arrows indicate control direction, and boxes represent actions. Flowcharts are used in planning to organize thinking. They help identify potential problems before coding. Flowcharts use specific symbols for clarity. Ovals mark the start or end, and parallelograms represent input or output. Rectangles indicate processes, while diamonds show decisions. Arrows guide the flow between steps. These symbols make processes easy to interpret. Flowcharts provide visual clarity and help analyze problems. They improve communication between teams. Flowcharts act as documentation for maintenance. They save time by ensuring logic is correct before coding. Flowcharts are vital in software design and problem solving. Consider an algorithm to find the largest of two numbers. The flowchart starts with inputting two numbers. A decision checks which number is larger. It outputs the larger number and ends. This visual representation clarifies the algorithm's logic. In conclusion, algorithms are the logical core of computing, providing structured and efficient solutions to complex problems. Understanding their principles enables effective problem solving and the development of optimized programs. Flowcharts play an important role in visualizing algorithms, ensuring clarity, accuracy, and precision in design. By mastering these concepts, programmers can create innovative and reliable solutions, driving progress across all areas of technology. Thank you for watching this video. If you have any questions, please feel free to send a message via WhatsApp at 07000 484 361,688. Thank you for your attention and see you soon.